This is your presenter Asloob Mudassar, and I am presenting slide number 51 of the course on laser physics. Question is, particles in gaseous state, for example atoms, molecules, may be excited, de-excited during a collision process known as non-radiative process. Discuss the rate of decay equation of the excited particles undergoing non-radiative decay process. Answer is, excited particles may decay through a non-radiative process, also known as collisional deactivation. Collisional deactivation occurs in excited particles present in a gas or liquid through the following mechanisms. Number 1. Energy is released as excitation of the colliding particles. Number 2. Energy is released as a transfer of a kinetic energy to the colliding particles. Number 3. Released energy is transferred to the container walls. Let us designate A and B star as one of the colliding particles in an unexcited state and excited state respectively. That is, the particle A is in the unexcited state and the particle B star mean that B is in the excited state. In an exothermic process, delta E appears as the kinetic energy of the particle A. For example, look at this reaction. B star plus A, that is B star, that is B is in the excited state, collides with particle A in the unexcited state. So these two particles collide with each other as shown by the plus sign on the left hand side of the arrow. And on the right hand side of the arrow we have B plus A star plus delta E. That is, after the collision, B is de-excited whereas A is excited, and also some extra energy will appear to the system, that is delta E is given off to the system, and this delta E may appear as the kinetic energy of the particles. For example, the excited particles may attain this energy delta E. Here we are assuming that the B star has more energy as compared with A star. That is, when the particle B is in the excited state, it has more energy in comparison when the particle A is in the excited state. So you see that again, let me let me say something about this equation is that on the left hand side we have a B star plus A, which means that these two particles collide with each other, and after the collision the particle B is de-excited and the particle A is excited, and also some energy delta E is given off to the system, and here in this case we may assume that this delta E will appear as the kinetic energy of the particle A. This type of collision is called collision of second kind, also known as the superelastic collision. In a reverse process, kinetic energy of the colliding particles may be converted to excite one of the particles. So you see that now we are going to discuss the reverse process in which the kinetic energy of the colliding particles will be able to excite one of the particles. For example, over here B plus A star, so the particle B which is in the unexcited state will collide with particle A which is in the excited state, and during this collision both of them has some kinetic energy. So when the collision will take place, then after the collision the particle B gets excited and A gets de-excited, and this minus delta E means that some energy has been taken from the system and then given in the process of excitation of a particle B. And this delta E is actually, you may assume that it could be the kinetic energy which is taken from the colliding particles and is given off to particle B for the excitation of this particle. And you see that the available energy will come from during the de-excitation of a particle A, and also from the colliding from the kinetic energy. So these two energies will help to excite particle B. So that's why we are using minus delta E over here. It means that the kinetic energy of the colliding particles has been used up in the excitation of the particle B. And of course some energy will also be available from the de-excitation of a particle A, which has also been used in the excitation of a particle B. So both energies here are involved, that is the energy released from the de-excitation of a particle A and also from the kinetic energy of the colliding particles. These two energies are used up in the excitation of a particle B. So we have used B star plus A minus delta E on the left hand side of this arrow. This process is called collision of a first kind, also known as thermal activation of a particle B. To discuss the rate of decay of an excited particle through non-radiative means, let's designate B star, NB star, as the population of the excited particle B star at time t, and Na as the population of the unexcited particle present at time t. So you see that now we are going to discuss the population of the excited particles, which is Nb star, and the unexcited particle, which is Na star. And for example, in a two-level system, this will be N2 star, and the other Na will be equal to N1. So Na will correspond to the ground state, and Nb will correspond to the Nb star will correspond to the population of the excited state. The rate of decay of the excited particles under the collision of second kind alone is given by. So here in equation number 51.1 we are going to discuss the decay rate of the excited particle which involves only second kind collision. So we have d Nb star over dt is equal to minus Kb star A multiplied by Nb star multiplied by Na. So you see that this rate of decay will be proportional to the population in the excited level, which is Nb star. And also it will proportional to the population of the ground state, which is Na, because the particles in the ground state will be available as excited particles in state will be available in the excited state. So we have dNb star over dt will be proportional to the two quantities Nb star and Na, and we have used some constant Kb star A. And this negative sign means that the population of the excited state, that is d and b star over dt, will decrease. That's why there is a negative sign. And Kb star A depends on the transition particles A and B star, including the effect of collision of first kind. Equation 51.1 can be written as. So in the above equation, that is the equation number 1, we are now going to include the collision of first kind, and that has been represented in red, the second term on the right hand side of equation number 2. So we have dNb star over dt is equal to minus Kb star A Nb star into Na plus Kba into Nb into Na. So you see that this will depend due to the first collision, first kind of a collision. Of course, we have the population Nb and Na. Both are in the state. That is the population of Nb and Na we have shown. So the first kind of collision will depend, that is dNb star over dt will be proportional to Nb and Na, and there is a positive sign over here. It means that due to this term, that is due to the red term, this dNb star over dt will increase, but due to the blue term which has a negative sign, this dNb star over dt will decrease. So one term in red will increase dNb over dt, and the other term which is in the negative will decrease Nb star over dt. Now Kba describes the process of thermal activation. Assuming the particle B are in thermal equilibrium with the particle A, so you see that when they are in thermal equilibrium, then it means that d and b star over dt will be equal to 0. Okay, So assuming that particle B are in thermal equilibrium with the particle A, then according to the principle of detailed balance, the rate of any process is balanced by its corresponding reverse process, that is KB star A NB star into NA is equal to KB into NB into NA. So these two will be equal to each other. That is equivalently you can say that NB star over dt will be equal to 0 under thermal equilibrium. Now we can also write down from here, from this equation, that is from this equation we can write KB star A is equal to KB into NB over NB star, and we have called this as equation number 3. For the particle B in thermal equilibrium with non-degenerate levels. So assuming that there is no degeneracy and the system is in equilibrium, under that condition we can write the population of the excited state, that is NB star, can be written as NB multiplied by e to the power minus delta E over KT. So this is what we can write for the system for the particles A in thermal equilibrium and having non-degenerate levels. So equation number 51.3, which we have written over here, can also be written as KB star A is equal to KBA into e to the power delta E over KT, because here we have substituted the ratio NB over NB star has been substituted by NB over NB star taken from equation number 4, and then we can rewrite equation number 51 with the help of equation number 52 as given in equation number 5. So we have KB star A is equal to KB into e to the power delta E over KT, where delta E is the excitation energy of a particle B. Capital T is the temperature of the mixture containing A and B particles. From equation number 5 we can write KB star A much greater than KB under thermal equilibrium, and when delta E is greater than KT, the process of thermal activation can be neglected, and NB star and NB will have the same order of magnitude. That is the magnitude, that is the order of a magnitude of these two populations, that NB star and NB will have the same order of magnitudes. So equation number 51.6 can be modified as, so we can multiply the left hand side of this inequality by NB star, and we can multiply it by the right hand side of this inequality by NB, because NB star and NB have the same order of magnitude. So multiplying these two quantities, these different quantities on the left hand side and on the right hand side, we obtain this expression, that is KB star A into NB star is much greater than KBA into NB. And equation 51.2, that is this equation, will reduce to the following form, that is this one. That is this equation. So you see that this term, which is the term in blue, since becomes much greater than in comparison with the term on the term shown in red on the right hand side of equation number 2. So we can neglect the term in red in comparison with the term in blue, and we can write the final term as dNB star over dt is equal to minus, is approximately equal to minus KB star A into NB star into NA as shown in equation number 7. Thermal activation cannot be neglected. So look at this very important sentence, that here you see that we have neglected the thermal activation. In writing equation number 7, we have neglected the thermal activation. But you see that if thermal activation cannot be neglected when the transitions involve rotational levels of the same vibrational level. So you see that if we are using molecular physics, then of course we have the vibrational levels, and for each vibrational level there could exist many rotational levels. and when the transitions involve rotational levels of the same vibrational level, then of course the thermal activation cannot be neglected and equation number 7 cannot be written. So for a two-level system, equation number 7 takes the form. So we can write 2 instead of B, and we can write 1 instead of A. So we can write dN2 over dt is equal to minus 1 over tau nr multiplied in the numerator by N2. So this is the rate of decay in terms of the time we are using, that is the non-radiative lifetime. So tau nr is actually the non-radiative lifetime, and this equation is what we have written independently, that is dN2 over dt is equal to minus 1 over tau nr multiplied by N2. So this becomes the rate of decay equation for the population in level 2 through the process of non-radiative decay, where N2 is the population of level 2. So we can now compare equation number 51.7 with this equation, that is dN2 over dt can be compared with the equation number 51.7 when it is written for a two-level system. Then according to that one, then the comparison will reveal that the time tau nr can be written as tau nr is equal to 1 over kb star a into nb star. So this tau nr is actually the lifetime of level 2 due to non-radiative process. And this is what we wanted to find out, the relationship for the decay of the excited state, and we wanted to find the lifetime of the non-radiative decay process. Equation number 51.4, which is this equation, 51.4, this equation can still hold for non-equilibrium condition provided the population of a particle B is maintained by a pumping process along with the translational degrees of freedom are still in equilibrium. So here we are not talking about the vibrational degrees of freedom or the rotational degrees of freedom. We are now talking about here that the translational degrees of freedom should be in thermal equilibrium, and that the population of a particle B is maintained through the pumping process if we want the equation number 4 to still hold. So this is the end of slide number 51.